As it turns out, let's look at an example where we can start to use what we've done. Given that this solution, y1 is e to the 2x, and y2 equals a negative, or e to the negative 2x, they're both solutions of the differential equation, and here's the differential equation, y double prime minus 4y equals 0 on R, on all real numbers. Show that they are linearly independent and find the general solution. Well, if they're linearly independent, the general solution won't be much, but we need to verify they're linearly independent, so we find the Wronskian. So the functions themselves, e to the 2x and e to the negative 2x, go in the top row, and we're going to find the determinant. And the second row is going to be the derivative of this, which is 2e to the 2x, and the derivative of this, which is negative 2e to the negative 2x. So if we multiply this by this, we get negative 2 times e to the 0, which is 1, of course, minus 2 times e to the 0 again, so the whole thing is negative 4 and not 0. Therefore, they are linearly independent, and if they are linearly independent, then they form a fundamental set of this second order equation. And being a fundamental set of the second order equation, then a constant times one of the solutions plus a constant times the other of the solutions is the general solution to the equation. That's going to be a big part of our solution. So, for differential equations in future, actually in the very next unit. So what's called a particular solution is any function y sub p that satisfies the non-homogeneous equation. See? G of x here instead of 0. That's called a particular solution of the differential equation. So the general solution of a non-homogeneous, you know what that means, right? This is g of x, not 0, is the solution of the homogeneous equation, so the fundamental set for the homogeneous equation, and further, a particular solution is added. Now look, this is what this is saying. If we've got our fundamental set for the homogeneous equation, and this is the general solution applied to that homogeneous equation with fundamental set, and yp is some particular solution to the equation, then all we have to do is add up the linear combination of our fundamental set plus the particular solution, and we have our general solution to the equation. And I hope you realize how cool that is. Oh, well, sorry, I didn't think it would be that boring. But let's look at an example. Much involved, but if you get this, you'll get almost everything so far. Verify that the two-parameter family of solutions, y equals c1 cosine x plus c2 sine x plus x times the sine of x plus cosine of x times ln of cosine of x, is the general solution, right? The general solution of the differential equation y double prime plus y equals secant x on the interval from negative 2 pi, or negative pi over 2 to pi over 2. Now, this is a deceptively simple looking equation, okay? But to verify, we first need to know that this forms a fundamental set for our homogeneous equation. So, all right, well, if y equals cosine x, then y double prime equals negative cosine x. So y equals cosine x is the solution to this equation. Similarly, if y equals sine of x, then y double prime equals negative sine of x. So that's also a solution for the equation. And they do form a fundamental set, because the Wronskian of cosine of x and sine of x turns out to be cosine squared of x plus sine squared of x, which equals 1. So now we know this linear combination of sine and cosine of x is the general solution to the homogeneous equation. That's the easy part. Here's the ugly part for this problem. We need to verify the particular solution to the non-homogeneous equation where yp equals x times the sine of x plus cosine of x times ln of cosine of x. You'll notice this is the yp because there's no constants attached here or here. No linear combination. It's just that is the particular solution. Well, if this is yp, then y prime of p, which was hard for me to notate with my software, but I did, first d second, that's x cosine of x, plus second d first, that's sine of x, plus first d second would be let me work my way through this. It's tricky. Cosine times ln of cosine. Well, the derivative of ln of cosine happens to be 1 over the cosine times the derivative of the inside function, which is negative sine of x. So I think I might have a slight sign error here. Oh dear. And I think I fixed it there because I want to say it's first d second plus second d first. I did that. That's the derivative of this first term. The derivative of this term would be first d second, which I think would be negative sine x over cosine of x, because the derivative of ln is 1 over the, but then we got to multiply that by the derivative of the inside function, which would be negative sine of x. So then plus second d first. Well, the second d first is just going to be ln cosine of x times sine of x. So, well, looks like I got the sign in there wrong also, so bear with me a second. In fact, I don't have the sign there wrong because the derivative of cosine is negative sine, so that part is correct. So the simpler version of that, notice because what cancels out here? Something does. We got a sine here, and this multiply to 1, so a negative sign here, so that cancels out. So what we really have is just x cosine of x minus ln of cosine of x times sine of x. So everything else canceled out except for this. That's y prime. Now we need y double prime and see if we can add it to yp and get 0 out of this. So let's see, not 0, we need secant x. Oh dear. That's right, because we have to make this equal to secant of x. So let's see if this is going to be verifiable. It's not an easy one, but let's do it. The derivative of this, first d second, so negative x sine of x, plus second d first, so plus cosine of x. No problem with that. And minus first d second. Recall we did this before. Ln of cosine of x is 1 over cosine of x times negative sine of x. So there's that part. And then what do we have? Oh, plus second d first. The derivative of negative sine would be negative cosine. So this mess, and let's hope something simplifies a little bit. Well, it does not. Does it? No, it doesn't. It's just going to be kind of ugly. Although I'll say this, we have a negative here and a negative there, that makes a plus, and we have sine of x over cosine of x, that makes a tangent x out of that term. This part's pretty straightforward. Now what about this part? There's not much I can do with that. But now we can substitute this y double prime into the equation, this one, right, the original equation, and if we do that, we get this big thing we just had, plus our yp, and we can simplify that. Let me see what cancels out, if anything. I hope some stuff cancels out. Look, we got a positive x sine of x and a negative x sine of x. Isn't that great? And we have, what else? Negative cosine x, ln cosine x. Look, here's positive cosine x, ln cosine x. What could be better than that? Oh, isn't that great? So what else now? So we just are down to cosine of x, which didn't cancel out, plus sine of x times tangent x. Everything else canceled out. But now, wait. Tangent x is sine over cosine, and if we find a common denominator of cosine of x, this would be cosine squared of x plus sine squared of x, all that over cosine of x. And cosine squared of x plus sine squared of x is equal to 1, and 1 over cosine x is equal to secant x. Therefore, we verified that yp is a solution. Great.